I want to show you how one can obtain a speed up of about 30/40 for performing a very simple task, namely the weighted sum of a number of k, here 90 matrices. I generated data as follows. Here I have matrices as a random 3-dimensional array. Each matrix has sign n times n. Weights is a simple vector, a 1-dimensional vector of k positions. And I compute the weighted sum in the most standard schoolbook manner. For each element ij I care about, I compute a weighted sum between what? The element of each matrix P at position ij, where P scans all matrices from 1 to k, and I sum these elements. Notice how the element ij of matrix P is multiplied by the associated weight. And let me see the running time, show you the running time of this. It's about 2 seconds, and I just want to tell you that in Julia this can be close to 20. So the speed up will be even huge if we compare to Julia. Now, many people may say that it is well known that in the most modern languages, the for loop are not very efficient where compared to calling some libraries that are highly optimized for speed. So let me show you a second solution where I call, so here I call sum. There is no list comprehension feature as in Julia to be able to use the for loop here, so maybe this reshape will take some time, but what do I do here? I reshape the weights to become a 3-dimensional array just as matrices, and using this operator I perform a pairwise multiplication so that each element of each matrix is multiplied like here by the corresponding weight, and finally I sum up the result according to the third dimension. So, as for the program above, I print some value just to be sure we obtain the same calculation for each method. Let me see the running time. I am at 0.3 seconds, so compared to 2 seconds, the speed up is less than 10. And let me now show you a last solution that may escape the attention of many, because it does not really explicitly call an existing method from some library, but basically I call a standard matrix vector multiplication. Let me show you the code. It takes 3 lines. Okay, what do I have here? The matrices are reshaped to become a 2-dimensional array in which I have k columns, so 1 column per matrix. Each column will be a vector of size n square. Then the main calculation is performed by this matrix vector product, and I obtain the result as a 1-dimensional array. Okay, so I need to reshape back this 1-dimensional array as a 2-dimensional one, and I print the same position for 5 of the resulting value. Let us check the running time. As you can see, I am at about 0.01 seconds, so please remember that we started from 2 seconds, so it's a speed up of larger than 20, and if I execute this again, I obtain a running time of 0.06 or 0.07 seconds, which is a speed up of around 30 something. And if we just wanted to be sure, let me execute again the very first approach to see if there is no huge variation like for the last one. Okay, so I'll execute this, and I think it will take again around 2 seconds. So again, if I compare this and this one, the speed up is between 30 and 40, maybe around 32. And just remember, as I told you, the calculation using for loops in Julia is 10 times slower than this one. And I have another video on YouTube where I show you that Julia can be actually the faster method when using this approach, because instead of 68 milliseconds, Julia can do it in around 30 milliseconds. So what's interesting, Julia can be twice as fast when implementing this approach, and around 10 times slower when using the classical old school book for I4J loops. Bye bye.